In this video, we will look at the principle of conservation of momentum, and we'll apply the principle of conservation of momentum to a few questions. Now, before we start looking at the principle of conservation of momentum, we must recall that momentum is defined as a product of a body's mass and velocity. So therefore, this means that momentum P is equal to mass m times velocity v. So momentum is a product of a body's mass and velocity, and therefore momentum is calculated by multiplying a body's mass by its velocity. Now, mass is a scalar quantity and velocity is a vector quantity. Now, momentum is a vector quantity, and therefore this means that being a vector quantity, it has both magnitude and direction, and this also means that basically if in one direction a body's momentum is being treated as being positive, then in the opposite direction another body's momentum will of course be treated as being negative. And when of course it comes to applying the principle of conservation of momentum to situations, we must always remember that. So if we're dealing with two bodies which are moving in opposite directions, then one body's momentum will be assumed to be positive, or its velocity, and the other body's momentum and its velocity will be assumed to be negative, due to the fact that momentum is a vector quantity. Right? Now, with that said, we will look at a few questions in which we'll apply the principle of conservation of momentum. Right? Now, what exactly does the principle of conservation of momentum state? Right? Before we look at the questions, according to the principle of conservation of momentum, when bodies in a system interact, their total momentum remains constant, provided that no external resultant force acts on the system. So I repeat, when bodies in a system interact, their total momentum remains constant, provided that no external resultant force acts on the system. Now, what exactly does this mean? Now, the word interact basically refers to collisions as well as explosions, right? So interaction, as mentioned, or the word interact as mentioned in the principle of conservation of momentum, refers to both collisions and explosions rather. So what exactly is a collision? A collision basically is where two bodies which are initially separate then come together, right? So a collision is essentially where two bodies which are initially separate then they come together, right? Such as, for instance, two vehicles in a motor vehicle accident. So they were initially separate, they come together, so therefore they collide, right? So when we speak about collisions, we're speaking about bodies which are initially separate and then they come together. Now, when we speak about explosions, it's almost the opposite. So with an explosion, the bodies are initially together and then they separate or they come apart. And an example of an explosion is a bullet being fired from a gun. So basically, the principle of conservation of momentum refers to both collisions and explosions, both of which are collectively referred to as interactions, right? So when we speak about bodies interacting, it simply means that they could either collide or they were initially together and basically they explode and then separate, right? Now, the principle of conservation of momentum basically deals with a before and after situation. So what is basically done is that the total momentum before the interaction is examined and the total momentum after the interaction. And basically what the principle of conservation of momentum is essentially saying is that provided no external resultant force acts on the system, then the total momentum before interaction is equal to the total momentum after interaction, right? So in simple form, this is basically what the principle of conservation of momentum is saying, that provided that no external resultant force acts on the system, then the total momentum on the bodies which are part of the system, so the total momentum before interaction is equal to total momentum after interaction. And if we have, say, a body 1 with a mass m1 and initial velocity u1, and of course a body 2 of mass m2 with an initial velocity u2, then the total momentum before interaction is given by m1 u1 plus m2 u2. And of course, if after the interaction the body's masses of course remain constant, we'll always make an assumption, right? So the body's masses remain constant and so therefore after the collision, the mass of body 1 is also m1. Its velocity would have changed to v1, and similarly for body 2, its mass is m2, and its velocity would have changed to v2. So what this is basically saying is that provided that no external force, resultant force acts on the system, the total momentum before interaction equals total momentum after interaction. So again, if we deal with bodies of masses m1, m2, which initially move with speeds u1 and u2, that is before the interaction, and then after they move with speeds or velocities v1 and v2, then therefore this means that m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So this equation basically sums up the principle of conservation of momentum, but based on the situation, of course, this equation may be modified somewhat, but generally this equation sums up the principle of conservation of momentum. So we will deal with situations, for instance, where one body is initially stationary, and for instance that would mean that its initial momentum is 0. So either one of these two terms, of course, will be equal to 0. We will also deal with situations where both bodies initially are stationary, and then therefore the total momentum before the interaction will be equal to 0, right? And an example of such a situation is a gun firing a bullet. So before the bullet is fired, both gun and bullet are stationary, and therefore the initial momentum is 0. But of course, because momentum must be conserved in all interactions, it therefore means that the total momentum after the interaction or after the firing will also be 0, and we'll generally use that to find the unknown velocity of either the gun or the bullet after the bullet is fired, right? So having said that, we will now look at questions where we need to apply the principle of conservation of momentum. So we're looking at questions from our worksheet on the principle of conservation of momentum, and we'll start by looking at question 1, right? Now, as mentioned before, momentum, or the principle of conservation of momentum, deals with a before and after situations, right? So this question says, a fully laden Range Rover Evoque of total mass 1800 kilograms, traveling at 20 meters per second, collides with a smart car of mass 850 kilograms. Assuming the two vehicles separate after impact, calculate the velocity of the Evoque if A, the smart car is initially stationary and its velocity after impact is 10 meters per second. So let's examine part A before we look at part B and C. So this question has 3 parts basically, and it tells you different situations, and we'll look at them differently. So in situations like these, what we normally do is to assign a body the subscript 1 and another body the subscript 2. So in this case, we're dealing with a Range Rover Evoque, which is going to collide with a smart car. So let the Range Rover Evoque be body 1, and therefore we can say that the mass of the Range Rover Evoque M1 is equal to 1800 kilograms, right? Now we're told it is traveling with a velocity, or traveling at 20 meters per second. So we'll take that value at its initial velocity, u1 is equal to 20 meters per second, right? Now it's going to collide with a smart car of mass 850 kilograms. So let the mass of the smart car be m2, and therefore m2 is equal to 850 kilograms. So basically we're given that information for the situation, and the rest of information of course depends on the what happens after impact, right? And also alright, so in part A, what we're told is that the smart car is initially stationary and its velocity after impact is 10 meters per second, right? So in part A, so this information refers to the entire situation. However, we're given different information for part A, part B, and part C, and of course we'll consider them separately, right? So for part A now, we're told that the smart car is initially stationary. Now if the smart car is initially stationary, this means that its initial velocity u2 is equal to 0. Again, we're using subscript 2 to represent the smart car and subscript 1 to represent the Range Rover Evoque, right? So also we're given that the velocity of the smart car after impact is 10 meters per second. and therefore this means that v2 is equal to 10 meters per second. And they want us to find the velocity of the Range Rover Evoque. So basically what we require to find is v1. So of course we're going to assume that momentum is conserved, right? So as a matter of fact, in all the collisions and interactions that we will deal with at this level, of course, momentum will be conserved, right? But generally in questions you have to state that momentum is conserved, or assume that momentum is conserved, and therefore state the principle, right? So we're going to say that basically since momentum is conserved, the total momentum now this is a collision, so we can say total momentum before collision equals total momentum after collision. Right? So usually we just write down the standard equation for the principle of conservation of momentum, and we'll then basically modify it accordingly. So we can write that m1u1 plus m2u2 is equal to m1v1 plus m2v2. Now in this particular situation, the Range Rover was traveling with a particular speed, and it's going to collide with a smart car. In this particular case, first case scenario, the smart car is stationary, and after the collision it moves at a velocity of 10 meters per second. So before the collision, the Range Rover is moving, but the smart car is stationary. Now if you remember, we said that momentum is a vector quantity, and therefore has both magnitude and direction. So therefore, if we're dealing with bodies moving in opposite directions, then it means that in one direction a body's velocity is considered to be positive, and hence its momentum, and in the opposite direction the body's momentum is considered to be negative, and hence its momentum is negative as well. So in this particular case, however, only one body is initially moving, so we don't need to be concerned about whether one is going to be negative or positive. The one which is initially moving will just be given a positive velocity, right? So m1 in this case is 1800, u1 is 20, and so we have 1800 times 20 plus the smart car is initially stationary, and therefore its initial momentum m2u2 is 0, and this gives us m1 still 1800. We don't know the velocity, of course that is what we want to find, so this is 1800 times v1, and this is plus 850 times 10. So after the collision, the smart car's velocity is 10 meters per second. So we try to work this out and solve for v1. So 20 times 1800, 2 times 18, that's 36. So we have 36,000. So this would be kilogram meters per second. I mean, we don't always have to put the units because you understand the momentum. As long as you basically put the unit of whatever we're calculating at the end, everything is okay, right? So 36,000 will be equal to 1800 v1 plus 8,500, right? So you bring the 8,500 across and you subtract it. So you get 36,000 minus 8,500, and that is equal to 1,800 v1. And so this gives us 27,500 is equal to 1,800 v1, and this therefore means that v1 is equal to 27,500 divided by 1,800, and that gives us 15.3 meters per second. Right? So this shows us that, or this gives us that the velocity of the Range Rover after the impact is 15.3 meters per second. Now let's try to analyze the situation a little bit. Now before, the Range Rover was moving at 20 meters per second and the smart car was initially stationary. After the collision, the smart car moved at a velocity of 10 meters per second and the Range Rover, as evoked, as we calculated, moves at a velocity of 15.3 meters per second. Now, if we examine the velocities of the Range Rover evoked before and after, we see that before it was a positive 20, and after it is also, well, positive. So what this basically tells us is that the Range Rover, after the collision, is moving in the same direction as it was moving before the collision. And that is expected basically, right? So because the smart car was initially stationary, the Range Rover, upon colliding with it, would have slowed down somewhat, but of course it would still be moving in the same direction. And it worked out that it moving with a velocity of 15.3 meters per second, right? So that was part A of the question. Now let's look at part B. Now part B says the smart car's initial velocity is 12 meters per second and in the same direction as the evoke, and its velocity after collision is 18 meters per second, right? So in part B, so this information from before still applies, the masses of course and the initial velocity of the Range Rover. So in part B now, we're told that the smart car's initial velocity is 12. So therefore this means that U2 is equal to 12 meters per second, and we're told that after the collision its velocity is 18 meters per second. So therefore this means that V2 is equal to 18 meters per second. So once again, we'll say that since momentum is conserved, total momentum before collision equals total momentum after collision. But of course, to avoid writing all of that repeatedly, I will just say it and I'll just write down the equation and then substitute the values, right? So once again, since momentum is conserved, total momentum before collision equals total momentum after collision, and therefore we have that m1u1 plus m2u2 is equal to m1v1 plus m2v2. So this time, once again we substitute the values. Now the initial velocity of the Range Rover is the same as from before, so therefore its initial momentum is going to be the same, 36,000. So we have 36,000 plus 850 times 12, and that is equal to 1800 V1 plus 850 times 18, right? So we have 850 times 12, so this gives us plus 36,000, so 36,000 plus 10,200, this is equal to 1800 V1 plus 15,300, right? So we add these all up, we get 47,200 equals 1800 V1 plus 15,300. And since we're solving for V1, we have to first bring this 15,300 over to the other side and then of course proceed. So 47,200 minus 15,300 all over 1,800 would be equal to V1. And so this gives us 17.7 meters per second. So therefore V1 equals 17.7 meters per second. And once again, the what was that V1? This should be, yes, V1, right? So once again, the velocity of the Range Rover is positive, and this therefore means that the Range Rover is still moving in its initial direction of motion, right? So when it comes to momentum problems, we can actually use the sign of the body's velocity to get an idea of the direction in which the body is actually moving, right? Oh, I made a slight error here. This should be 46,200. So this should be 46,200. So this should be this works out to be 17 points. Not big difference, but I just want to be correct. 17.2 meters per second, right? Alright, so that was part B of the question. Now let's look at part C of the question. In part C of the question, the two cars become stuck together in the impact, and the smart car's velocity, or smart car's initial velocity, is 15 meters per second in the same direction as the evoke. So we'll take off just what we don't need. So let me take off that. Alright, so in this particular case, so let me take this off. So we're told that now the two cars become stuck together in the impact, and the smart car's initial velocity is 15 meters per second. So this means that U2 is equal to 15 meters per second. Now we're told that the two vehicles become stuck on impact. Now if they basically become stuck, then it simply means that after the collision they move together as one body, and therefore they move with the same velocity. So therefore we can say that V1 is equal to V2, and let's just call that velocity V, right? So for the purpose of this, we can say that, of course, because they're stuck together, they will move together as one body, and they move with one common velocity. And so therefore this means that V1 equals V2, and let's call it common velocity V, right? So once again, momentum is conserved, and the total momentum before the collision is equal to total momentum after the collision. So M1U1 plus M2U2 equals M1V1 plus M2V2. That's our standard form of the equation which governs the principle of conservation of momentum, right? And so once again, this is 1800 times 20. In the case of the smart car, it is moving with an initial velocity of 50 meters per second. So therefore 850 times 12, this goes here. This is plus 850 times 12. And over here now, they basically move together. So again, once we said that V1 equals V2 equals V. So this gives us 1800V plus 850V. And to work out these, so this is 36,000 from before. Actually, this should be 15, not 12. This is 15 or 12. So 10, that's 8,500 plus 4,250, that's 12,750, and this is equal to 2650 times V. And so we get 48,750 is equal to 2650V, and therefore V is equal to 48,750 divided by 2650, and this should give us 18.4 meters per second. Right? So in this particular case, the two bodies become stuck upon impact, and they move together collectively as one body, and therefore their velocities after the impact are equal. So therefore we modify the equation so that V1 equals V2. I would simply let that be common velocity V. Now this type of collision is referred to as what is called a perfectly inelastic collision. So a perfectly inelastic collision is where the bodies collide but they don't bounce off. They basically they become coupled together. So they stick together upon impact, right? So an inelastic collision basically is one where kinetic energy is not conserved. And most collisions in nature are inelastic because there is usually some loss of kinetic energy upon impact. So therefore kinetic energy is not conserved. So generally the term inelastic collision refers to collisions where kinetic energy is not conserved. When we speak about a perfectly inelastic collision, it also means that kinetic energy is not conserved, but it basically means that upon impact the bodies collide and they stick together. And of course an elastic collision is one where bodies collide and kinetic energy is conserved, right? And we shall look at one or two questions involving elastic collisions. Alright, so that was question 1 from our worksheet. We will proceed with another question. To avoid having to rewrite this, I'll leave it on the board. Alright, so this time we will look at question 2. Now question 2 says a railway truck A of mass 2 times 10 to the 4 kilograms traveling at 1 meters per second collides with a second truck B of mass 1 times 10 to the 4 kilograms moving in the opposite direction at 0.5 meters per second. If the trucks couple automatically on impact, calculate the common velocity with which they move after impact. So we're told that we have 2 railway trucks, A and B respectively. So once again, we will we'll assign the 2 B bodies subscripts and then we'll proceed. So we're going to let truck A be, let that be vehicle 1. So therefore the mass of truck A, M1, equals 2 times 10 to the 4 kilograms. And this truck, we're told, is moving with a velocity of 1 meters per second. So we're going to let U1 be 1.0 meter per second, right? We're told it collides with a second truck B of mass 1 times 10 to the 4 kilograms. So we're going to let M2 equals 1 times 10 to the 4 kg. And this truck moves in a direction, or moves in a velocity of 0.5 meters per second, but in the opposite direction. So because this truck is now moving in the opposite direction, well, we have bodies which are moving in the opposite directions. And so if we let the initial velocity of one body be positive, then the velocity of the other body must be negative. So whenever we're dealing with bodies moving in opposite directions and we know their velocities, we will let one velocity be positive and the other one, of course, be negative, right? And that must be the case because momentum is a vector quantity, and so on. So therefore, this means that U2 is equal to minus 0.5 meters per second, right? Now, what we're told is that the trucks couple automatically upon impact, and we want to find the common velocity with which they move after impact. Now, because they couple on impact, it means that basically after the collision, V1 is equal to V2, and once again, we're going to let that be equal to some common velocity, V, right? So basically, we can say that since momentum is conserved, the total momentum before collision is equal to total momentum after collision. So once again, we begin with our standard form of the equation and we'll modify it to suit, right? So what we have here now, 2 times 10 to the 4 times 1 plus 1 times 10 to the 4 times minus 0.5 is equal to, so the velocity is now common, so this will give us 2 times 10 to the 4 times V plus 1 times 10 to the 4 times V, right? So this becomes 2 times 10 to the 4 and this becomes minus 0.5 times 10 to the 4, so we get 1.5 times 10 to the 4, and this of course will be kilogram meters per second. I mean, we don't always put the units, as I said before, we can leave off the units as long as we put the units of whatever we're calculating at the end. So if we're calculating the velocity, then of course we must put meters per second and so on, right? And this of course will be equal to, so this V plus that V, this gives us 3 times 10 to the 4 V. And this therefore means that V is equal to 1.5 times 10 to the 4 kilogram meters per second divided by 3.0 times 10 to the 4 kilograms, and this gives us 0.5 meters per second. Now, many times when we are asked to calculate the velocity of one of the bodies which was involved in the interaction, right? I mean, it's not always a collision, could be a collision or an explosion, so collectively the term interaction applies. Now, in cases like these, of course, the sign of the velocity will give an indication of the direction in which the body is traveling. So in this particular case, we had a truck A, which denoted vehicle 1, and a truck B, which denoted vehicle 2. And they were traveling in opposite directions. And because they were traveling in opposite directions, we had to make one vehicle's velocity be positive and the other one be negative. So the bigger truck had a positive velocity, and of course the smaller one we gave a negative velocity. Now after the impact, the velocity with which they move together, that is their common velocity, is positive. And what this tells us is that the two trucks are moving in the same direction as that of the bigger truck, or that of the initial direction of the bigger truck. So what this is basically saying that the two trucks are basically moving in the same direction as the bigger truck was moving, and that is because the velocity turns out to be positive. If, however, if the velocity had worked out to be negative, then it simply would have meant that the two trucks would have been moving in the initial direction that we consider to be negative. So once again, we can actually tell the direction that the body is moving in based on the sign of the velocity that we actually calculate, right? So that was question 2 from our worksheet, right? So we basically look at two couple situations before. I looked at different situations where one body was moving initially and the other body was stationary, and then of course both bodies were moving, and then they became stuck on impact, and then they moved together, right? Now let's look at a situation which is not a collision, but this time an explosion, right? So we look at question 4 from our worksheet. So question 4 says, a gun of mass 2 kilograms fires a bullet of mass 50 grams. Calculate the initial recoil velocity of the gun if the bullet has a velocity of 300 meters per second, right? So as I mentioned before, principle of conservation of momentum deals with a before and after situation. So we must consider what was happening before and what is happening after a particular event occurs. In this particular case, we're talking about a bullet being fired from a gun. Now, before the bullet was fired, then both gun and bullet would have been stationary, and therefore this means that the total momentum before the firing would, of course, or before the explosion would have been 0, right? Now, once again, momentum is going to be conserved, and if the total momentum before the explosion is 0, then it also means that the total momentum after is also equal to 0. Now let's use a little diagram or simple diagrams to represent the before and after situations, right? So before, after. So I'll try my best to draw a gun or something resembling a gun. Right? So that's our gun there, and of course inside we have our bullets, right? So we have our bullets, and of course after we have our bullets being fired, certain velocity, and of course there is going to be a recoil, right? If you ever fire a gun, then of course you'll definitely know what the recoil is all about, right? So the recoil basically means that the gun is going to move in the opposite direction. So before, both gun and bullet are stationary, right? So both and bullet are stationary, right? So we can say that, for instance, if the initial velocity of the bullet be UB, then that will be equal to 0. Initial velocity of the gun, UG, that will also be equal to 0. Now after bullet is fired, we're told that the bullet moves off with a velocity of 300 meters per second, and we don't know the velocity of the gun, and that is basically what we want to find, right? So once again, this is basically an example of an explosion, and explosions and collisions collectively are referred to as interactions, and momentum is conserved in all interactions, right? So we can say that basically, since momentum is conserved, total momentum before explosion equals the total momentum after explosion, right? Now before the gun is fired, before the bullet is fired, we know that both the gun and the bullet are stationary, and therefore it means that their total momentum is equal to 0. So we don't need to put m1u1 plus m2u2 or anything like that, because we know that both bodies are stationary before the bullet is fired, and therefore what goes on the left hand side is equal to 0. So 0 is equal to, so if you let the mass of the gun be mg and the mass of the bullet mb, we're given that the mass of the gun, of course, is equal to 2 kg, and the mass of the bullet is equal to 50 grams. Of course, you convert that to kilograms, right? So it means that using the symbol 0 is equal to the mass of the gun times the velocity of the gun plus the mass of the bullet times the velocity of the bullet. Right? Now, the question one might be tempted to ask, how is it that both bodies are going to be moving and yet their total momentum is equal to 0? How is that possible? You must remember that momentum is a vector quantity, and if in one direction a body's momentum is treated as being positive, in the opposite direction its momentum must be treated as being negative, of course similar to velocity. And this is the principle which allows the total momentum of these two bodies to be equal to 0, right? So substituting the values, we can get that 0 is equal to the mass of the gun, which is 2 kgs, so let's just put 2 times the velocity of the gun. This is plus the mass of the bullet, 50 grams, so we convert that to kilograms, divide by 1000, that gives us 0.05. And the velocity, of course, is 300 meters per second, right? So we work that out, so we get 0 is equal to 2 Vg plus 300 times 0.05, that gives us 15, right? And this will be kilogram meters per second, of course. And so we get that 2 Vg is equal to minus 15, and therefore the velocity of the gun Vg is equal to minus 7.5 meters per second, right? So the velocity of the gun works out to be minus 7.5 meters per second. And since we assumed the initial velocity of the bullet was a positive 300, then basically what this shows us is that the gun will now be moving in the opposite direction. And once again, if you ever fired a gun, you would have experienced that recoil and you will have been pushed backwards, and that of course is due to the massive force or due to the recoil of the gun, right? So naturally we expected the gun to be moving in the opposite direction, and the velocity being negative confirmed this. So we look at one more question from our worksheet. Alright, this time we look at question 9. So question 9 says, a snooker ball X of mass 0.3 kilograms moving with velocity 5 meters per second hits a stationary ball Y of mass 0.4 kilograms. Y moves off with a velocity of 2 meters per second at 30 degrees to the initial direction of X. Find the velocity of V of X and its direction after hitting Y. And we're given we're given a diagram to represent this situation, and so I will draw the diagram, right? So we have a ball X, snooker ball X, moving with a velocity of 5 meters per second, right? It's going to collide with a ball Y, which is initially stationary, right? And after the collision, ball Y, so this is the initial direction of X. After the collision, ball Y moves off at an angle of 30 degrees to the initial direction of X with a velocity of 2 meters per second, right? And X moves off at some angle theta to its initial direction. And we're told the velocity is v. So this is the path of x and the velocity is v. Right? So basically this is an example of momentum in two dimensions. We're dealing with two-dimensional motion here. So similar to when we looked at projectile motion, we are dealing with two dimensions, or motion in two dimensions, and naturally that would involve some components, right? So we're going to have to deal with vector components, right? So let's analyze the situation. So this is basically our before situation. So this is the before and this is the after. So this is before. So before, x is moving at a velocity of 5 meters per second and y is stationary, right? So this of course will be 1. So x is going to collide with y, and after the collision, y moves off at an angle of 30 degrees to the initial direction of x with a velocity of 2 meters per second, and x after collision, it moves off at an angle of theta to its initial direction with a velocity v, and what we're asked to find is the velocity v. So before we do anything else, let's resolve these vectors into their respective components, right? So each velocity vector will have a component. Let's call this direction horizontal, and of course this direction vertical, right? So each of them will have a vertical component and a horizontal component. So this angle of course would be 30 degrees, and therefore this component is going to be in terms of the adjacent of the angle. So this is 2 cos 30 degrees. And this one of course would be 2 sine 30 degrees. Similarly, this velocity will also have two components. This is horizontal. This angle of course is also theta, and this is its velocity v. So therefore this is v cos theta, and this is v sine theta. So since we have motion in two dimensions, then what we'll have to do is basically our two directions, or same thing essentially, we'll have to consider each direction separately and apply the principle of conservation of momentum in that direction, right? So first of all, let's consider the horizontal direction. So horizontally, so once again momentum is going to be conserved, and we can say that total momentum before collision equals total momentum after collision. Right? So instead of using the M1, M2, M2, U2 subscripts, we'll use X and Y, right? So what we can say is that basically mass of X, initial velocity of X, plus mass of Y, initial velocity of Y, equals mass of X, initial velocity, final velocity of X, plus mass of Y, final velocity of Y. Right? So X, we're told that the masses, the mass of X, so the mass of X equals 0.3 kgs, and the mass of Y, we're told, is equal to 0.4 kilograms. Right? So let's substitute these values. So now we have 0.3 times 5 plus 0. Y is initially stationary, and therefore its initial momentum is simply equal to 0. Right? So this is equal to, now after the collision, mass of X of course is still 0.3, because we assume that the mass of course remain unchanged. Now the velocity of X would be, so we're talking about the horizontal direction, and therefore the horizontal component of X's velocity after the collision is v cos theta. So this is times v cos theta, right? And plus, now if you notice, after the collision, of course, as I said before, y moves off in that direction, x moves off in this direction. We resolve their velocities into their respective components, and you can see that the horizontal component of x's velocity, and the horizontal component of y's velocity, they both go in the same direction, and therefore we just treat them as being positive, since they're also moving in the initial direction of x, right? So this is 0.3 v cos theta for x, and then for y it would be 0.4 times 2 cos 30, right? And we try to simplify. So this gives us 15 equals 0.3 v cos theta, and this will be plus 0.4 times 2, 0.8 cos 30, so 0.8 cos 30, that gives us approximately 0.69, right? So of course we bring the 0.69 across, so we get 15 minus 0.69 is equal to 0.3 times v cos theta. Is that 15? Sorry, not 15, 1.5. Right, so 1.5 minus 0.69, that gives us 0.81 is equal to 0.3 times v cos theta. And if we divide both sides by 0.3, we get that v cos theta is equal to 0.81 divided by 0.3, and so therefore v cos theta is equal to, that would be 2.7, and we call that equation 1. So if you notice, we still have two unknowns, and we cannot solve a single equation in two unknowns. We need at least one other equation in those same two unknowns before we can actually solve it, and we'll have to solve them simultaneously, right? So to get that second equation, we know to consider the vertical direction of both bodies. So let's consider vertically. Now, vertically, momentum is also going to be conserved. And so we can say that since momentum is conserved, total momentum before collision equals total momentum after collision, right? So let's examine the vertical direction now. Now remember that the principle of conservation of momentum deals with a before and after situation. So we have to examine what is happening before, or what was happening before, and what happened after. Now before, only one body was moving, ball X, and it was moving what way? Horizontally. So therefore this means that vertically, the initial momentum is 0. So initially, only one object was moving, only one body, one ball was moving, ball X, and it was moving horizontally. And therefore this means that the initial vertical momentum is simply equal to 0, right? So instead of just writing down mx ux plus my uy, we know all of that is going to be equal to 0. So we can just write down that 0 is equal to mx vx plus my vy. And bear in mind that we're considering the vertical direction, so these subscripts x are not indicating the x direction, but simply the particular body. So x represents the ball x, and the subscript y for ball y. So the total momentum, total vertical momentum before the collision equals 0, and we'll have to now substitute the values and basically get a second equation, which we will solve simultaneously with that one. So what this gives us now, so vertically, x, as x is moving vertically downwards with a velocity of v sine theta. but y is moving vertically upwards with a velocity of 2 sine 30. So because bodies are moving in opposite directions, we have to assign one direction to be positive and one to be negative. And customarily, we take upwards or positive y as positive and downwards negative y as negatives. So we'll basically let this value be negative and that be positive. So the mass of x, which is 0.3, so this gives us 0 is equal to 0.3 times minus v sine theta. And this is plus 0.4 times 2 sine 30. Right? So we get 0 is equal to minus 0.3 times v sine theta plus, now sine of 30 that is equal to a half. Half of 2 that is simply 1, so this gives us 0.4. So basically, if we just bring one term to the next side, what we have is basically we get 0.3 times v sine theta is equal to 0.4, and this therefore means that v sine theta is equal to 0.4 divided by 0.3, right? So if we work that out, we get our second equation, which works out to be v sine theta is approximately equal to 1.33, and we call that equation 2, right? Now, having obtained the second equation, we'll then proceed to solving them simultaneously, right? So, continuing, let me just take off this first piece here. Let me just take off the entire thing. This. So using our two equations now, so we have an equation v cos theta equals 2.7 and v sine theta equals 1.33. If we were to divide these two equations, so we could say equation 2 divided by equation 1, we get that v sine theta divided by v cos theta, that would be equal to 1.33 divided by 2.7. The v's cancel, and of course, according to our trig identities, the sine of any angle divided by the cos of that angle, then this means that tan equals equivalent to the tangent of the angle. So tan theta equals 1.33 divided by 2.7. So that gives us 0.49. And therefore theta is equal to the tan inverse of 0.49. And so theta gives us 26.2 degrees. Right? So the angle that v makes to the initial, or x makes to its initial direction is 26.2 degrees. Now, having found the value of theta, we can then substitute the value of theta into either equation 1 or equation 2 and then solve for v. Right? So let's substitute it into equation 1. Right? So v cos theta equals 2.7. So v cos 26.2 equals 2.7. So v times, let's just write that out. So v equals 2.7 divided by the cos of 26.2 degrees, and v works out to be approximately 3 meters per second. Right? So therefore v works out to be 3 meters per second. Right? Now, we already took into consideration that this was a negative direction, and so basically when we added down negative signs and so on, then basically what we got was that it's just a magnitude of the velocity, right? So this basically gives us a magnitude of the velocity because we initially treated one of them as being negative for the vertical direction, right? So if we hadn't put the minus sign here, then the velocity of course would have worked out to be negative, right? And that would have simply meant that it was going in the opposite direction as y, which of course we already anticipated or we already knew, since we have already resolved the vectors into their components and showed the respective directions, right? So that was question 9 from our worksheet on principle of conservation of momentum. So just to summarize, in this video we stated the principle of conservation of momentum, what exactly it means for momentum to be conserved. We talked about momentum being a vector quantity, therefore having both magnitude and direction, and of course if in one direction the body's momentum is treated as being positive, in the opposite direction it has to be taken as being negative, right? And of course look at different situations in which bodies interacted, and we apply the principle of conservation of momentum to find a body's, say, final velocity and so on. Right, so that pretty sums up our look at momentum and the principle of conservation of momentum.